It tastes good.
Okay, we're live, guys. So a forum question was posted about this one, and when I saw it, I was like, oh, that's a cute problem. And then I tried to do it. So it's a little tricky, so I'll outline the solution. If anyone wants to try it.
Well, we have to try it.
Well, yeah, I was gonna say, if anybody wants
Everything's
to.
optional. You don't have to try it.
Well, I mean, okay, we have to if we want
It's
to.
just like 1 out of 1,000 points. So
College is optional. But every point counts.
College is
Every
optional.
point counts if the grade grade on the test is like lower than a 70.
Oh yeah.
She's got a point.
Okay. So first thing is just to find the area that curve contains with respect to the x-axis, right? And that's not too bad. This factors as x times 2 minus 5x. So the zeros of this are x equals 0 and x equals 2/5. Okay. So if I make a quick sketch of that, here's 0. Over here is 2/5. Did I do that right? Yeah, 2/5. There's 2/5. Axis of symmetry lives right in the middle, which would be at 1/5. And so this parabola does that. And whatever that line value is up there. I don't really care. Because you can easily integrate that, right, and get this area.
Yes.
All right, so that's no problem. So that's step 1. Okay, find that area, which is just the integral from 0 to 2/5 of 2x minus 5x squared dx. Oh, Google crash again? No? Is my pen freaked out? Okay. So then is where the exciting part comes in. So then you're said, hey, a line passing through the origin splits this area in half. So here's my best estimate at that line right there. If it passes through the origin, that means its y-intercept is 0, so its equation is just y equals some m times x. Okay. So that, whatever this area is, let's call it A, capital A, we get A over 2 down here, and we get A over 2 up here on each side of that line. All right, so how do we confirm we've got the slope, the right slope? Well, we'd have to integrate one of these halves. I think the top one is easier.
Yes.
Okay, why?
Yeah, why?
Because the parabola is always on top in that region right there. Yeah. So William, I'm going over your question that you posted to the forum. So if I draw a rectangle right here, right, as that rectangle slides back and forth, the parabola is always on top and the line is always underneath. Okay. So that means I would integrate to get A over 2, the parabola, 2x minus 5x squared, minus the line, mx, with respect to x. Problem, where does the integral start and end?
It wouldn't start, it would end at the 2.5.
Yeah, it wouldn't end at 2.5, it ends at wherever they meet. So I have to figure out where these two meet. Yeah. Well, no, you can actually solve that. So it's going to go from 0 to wherever they meet, right? So I'm just going to call that meeting point x1. All right, well, how do we find the meeting point x1? Well, you just set the red line equal to the blue curve and solve for x. And that's where they meet. So you would just say, hey, okay, to get this number x1 here, you would say, where do 2x minus 5x squared and mx meet? And you can solve for x, but you get an m stuck in there. So then what you end up with is an m as an ending boundary, and you've got this m sitting right there. And what's that? No, not yet. So what you do is if you have to find an antiderivative of this, that's not a problem. That's pretty easy. Okay. And then you have to plug in 0. That's nice. Right? Plugging in 0, it's all going to disappear in this case. And then you have to plug in whatever that number ended up being. Set it equal to whatever half the area is, and then solve for m.
Yummy.
That's
Okay.
annoying.
Yeah.
Wait, but
That's why.
So I have a solution on paper. It would take me way too long to type up, but I will show it right here. Let's see, where'd you go, Google? There you are, switch camera. Hello. So I will post my solution. It's right there. Cool, huh? It took me 3 tries to get it right. Notice I have red scribbles over pencil scribbles.
Can you just take a picture of it?
That's what he's doing.
Yeah, I'm gonna take a
I thought
picture
you were
of it
just gonna
and post it.
show it to the video and.
So again, you gotta graph it. Highly recommend graphing every time you do a problem from now on. Okay? You should draw a picture. Most of you are probably just gonna draw it on the computer and look at it.
Yeah.
I would highly recommend practice drawing it on paper, especially for those of you who are messy sketchers. The only way to be a good sketcher is to sketch more often. So back to the camera here. Yeah, so step 1 is you got to figure out what is this area here. Once you find it, you're trying to identify the line that gives you half of it. To do that, you have to find this intersection point.
That's like the part I'm so stuck on.
Solving this right here?
Yeah.
Okay, I'll do that part.
That and where does it? How do you get rid of the
So,
end
but I'm
in
not
the
gonna
interval?
do the whole thing. You don't, you're stuck with it.
You're stuck with it?
Yeah, so what's gonna happen is, first you find the intersection point by solving 2x minus 5x squared equals mx.
Okay.
Now, notice every term has an x in it,
Yeah.
which means x equals 0 is one of those numbers,
Okay.
which we already knew from the
Yeah.
picture. So we can divide that out.
Oh, okay.
So that gives me 2 minus 5x equals m,
Okay.
right? Dividing the x out.
Yeah.
Because we don't care if x is 0 here,
Right.
because we want the other x value. So then just solve this, right, for x. So then I would subtract 2 to the other side, so I get negative 5x equals m minus 2, divide by negative 5, so I get m minus 2 over negative 5. If the negative 5 on the bottom is freaking you out, then just switch the top and get a positive 5 on the bottom. So that's the intersection point based on the slope. That's my upper bound for my integral.
Oh, and then you put that into the interval?
Yeah, so then I have to integrate from
Okay.
0 to that number, 2 minus m over 5. And what am I integrating but, pretty much that thing on the top.
Right.
2x minus 5x squared
So then you just.
minus mx. Antiderivative in this case is going to be antiderivative of 2x
X squared.
would be just x squared. Antiderivative of 5x squared.
Negative.
X cubed.
Okay. And antiderivative of negative mx.
Mx squared over 2.
Mx squared over 2. Yeah. And then next thing we have to do is plug in 2 minus m over 5. Plugging in 0 is going to zero all of that out.
Yeah.
So basically you're just going to replace x
With 2
with this.
that. Oh.
And you're gonna solve for it.
And you got to set it equal to half the area. Whatever a over 2 ended up being. You got to find that in the first step. That one's
Okay.
Yeah,
So,
and then
okay, so
solve for
then
m.
you end up with just m's in the.
You just get m's, yeah. So
Oh,
this ends you get this equation with all m's equals some number. Maybe that number is 1.5. I don't know what it is. But it's
That
just
was
some
the
number.
part that I was like, how do I handle 2 different variables?
Yeah, and then I couldn't find any other way to do it. I asked a couple other people. They're like, I think that's the only way to do it.
Okay.
We were hoping there was some cute geometry trick you could throw at it. There's not that we found yet. So,
Okay.
Yes,
But-
check.
I have some other good minds working on this. If they come up with something better, I'll let you know. But that's the outline, yeah. So you just have to plug that in, figure out what A is, cut it in half, solve for M.
Okay.
That part right there would be like a really, really, really hard problem for Math 111. But it's doable.
So this is what Math 111 problem?
At this point, once I plug in the 2 minus m over 5, it's a Math 111 problem. It's just a hard parabola problem, a hard factoring equation to solve. It turns out you actually don't even have to factor. Things just kind of clean up nice. Well,
Okay.
relatively nice. Yeah. So I'll take a picture of my paper solution and post it. And it's okay if you don't get one problem right. You live. Okay, next. So all of these problems involve taking great care with your arithmetic, with your algebra. I showed a trick the other day for using GeoGebra or Desmos. Once you find your antiderivative, make it a function inside whatever program you're using, because then it makes evaluating the definite integral so much easier. Okay? And I'll use that in some examples in a minute, remind people on how to do that. For now, we are going to jump into the next section, determining volumes by slicing things up.
Oh dear. What
Yeah.
the?
Okay.
Is that legit what it's called?
What's that? Volumes by slicing. That is the title of this section. Yeah. So this is section 2.2. Volumes by slicing. And we're going to get really fancy. We're actually going to spin and slice, kind of like Ninja in 3D.
I don't like that.
But we'll start off just slicing. Yeah, totally ninja math. So first example we're going to look at is a pyramid.
No, never mind.
So I've got this pyramid and I want to find its volume. And let's say it's a pyramid with a square base, which is going to make my life a little bit easier. And let's make it 2 by 2 by, and give it a height of 3. So keep in mind the base of this pyramid is a square. Okay. So the slices that I'm envisioning are, oops, again, here we go. A slice through here, through the pyramid, parallel to the base. So I'm going to take these slices through the pyramid. Now, if that's parallel to the base, what is the shape of every single one of those cross-sectional slices? They're going to stay squares. As long as I stay parallel to the base, they'll stay squares. Yeah, if I rotate it a little bit, it would turn into some kind of rectangle. Depending on the rotation, maybe even a parallelogram. But as long as I stay parallel to the base, then each cross section is squared. Because the base is square.
Oh, the cross section, not the, I was thinking the sides.
No, I'm taking a cross section, so I'm just slicing right through here. So that blue thingy I just drew is parallel. It's a square viewed at an angle, my best interpretation of 3D.
Still similar to the original.
It's still a similar shape, yes, proportional to the original shape. Yeah, and that's the key to that proportionality. We've used that idea before. Remember when we were emptying out cones in related rates problems? This is really similar to the work we did there. Okay. All right, so I'm just gonna turn this on its side now because it's easier algebraically if I do that. So imagine that here's the XY plane, so there's X, here's Y. I'm gonna put the tip of the shape right there. And then, let's see, what did I say it was? 1, 2, 3 by 2. So, did I get that right? Yeah. Blue lines. So this is like staring at it sideways, straight on, without any perspective going on. Base here is from -1 to 1, so that length right there is 2, and the height in here is 3. Okay, so that's just like a head-on look from the tip, just rotating it sideways. So then imagine taking this line right here and projecting it perpendicular from the paper or the board to turn that into a square sticking out of the screen.
Okay.
Yes.
Imagine this line right here, and you generate a square by coming out perpendicular to the screen or your paper.
Okay.
Okay. So this thing right here is going to become a square. So this slice I have right here, that's say somewhere over here. So that is one edge of a square.
Okay.
Okay. So now I just need to find an equation for the length of that edge, which I can do because I have this lovely line running through there. What's the slope of that line?
1/3 x.
In this case, it's 1/3. Yes, this is y equals 1/3 x. So if you give me an x value, like whatever that x value is right here, then I can tell you that height right there, right? So how do I get this full height?
1/3 x minus negative 1/3 x.
Double it.
Which ends up doubling it, yeah. Yeah, so that's twice as big. So my edge of my square right here, so according to this picture, the square edge is equal to 2/3 x. How do I turn the length of the edge into the square's area? Multiply it by itself or square it. Okay. So what I found is that the area of this cross-sectional square right there, its area is 2/3 x squared. You tell me an x value, I'll tell you the area of that slice. Now, I'm going to turn that slice into a volume by giving it a little bit of thickness. Right? Does that line I drew have a little bit of thickness to it? Yeah. Very thin. I'm going to call that thickness dx. So if I take the area and multiply by a little bit of thickness, I now have a little bit of volume. Okay? So imagine like slices of paper that are square, and they get progressively smaller up to infinitesimally small at the top, and you stack all those papers together, you will make a pyramid out of sheets of paper. Can you picture it?
Yeah.
Right? We could take a notebook and stick it in a saw and make that happen, as long as the blade's very sharp. Right. All right, so here's what we got now. For this particular pyramid, drawing it to the best of my artistic ability, something like that, we've determined that a little thin slice perpendicular to the base has a volume. I'm going to call it delta V for delta volume. It's a little slice of volume. Is 2/3 times x squared dx. All I have to do now is integrate through all possible slices. And if you look back at my sideways version of the cross section, right here, x was going to go from 0 all the way to 3, right, which was the height of this pyramid. So I believe that if I integrate as x goes from 0 to 3, I'm going to square out that thing, and I'm going to call it 4/9 x squared dx. That this will give me the volume of the pyramid. So most of the work is in the setup. Is that an easy antiderivative to take? Yeah, the hard thing was setting it up. You got to draw pictures to set these up. I can't do it without drawing pictures. All right, help me out. What's an antiderivative here?
4/7 x cubed.
4/9 x cubed over 3, right?
Yeah.
And then we have to integrate that from 0 to 3. So notice how I'm relatively neat here, even though I'm not the neatest person. So when grading your tests, some of you are very sloppy in your notation. Try to tidy it up so it's easier for me to look at and give you a good grade. If it's messy and I'm not sure what you're doing, it's hard for me to give you a good grade. You know what I mean? So practice neatness. All right, plugging in 0 is nice. The lower bound is just going to vanish. So really, I just get the upper bound here. So that gives me 4/9 times 3 cubed over 3 cubed. Oops. Ooh, lots of stuff cancels here, right? 3 cubed is the same as 9 times 3, so it looks like the answer is 4. So the volume of this thing should be 4 cubic units, whatever those are. Maybe they're inches, centimeters. Let's go with centimeters. Let's be progressive. Oh wait, the rest of the world uses centimeters. I guess that's not being progressive, is it? We'll use them anyway. All right, so does anybody remember back from geometry class in their past a formula for a pyramid?
Oh,
1/3 base times.
1/3 area of the base times the height. Yeah, so let's apply that here just to double check. This pyramid was 2 by 2, and then it was 3 tall. So the volume should be 1/3. Area of the base is 4 times the height,
4.
which is 4. We just proved with calculus that the volume of a pyramid is 1/3 base times height.
There's a.
Otherwise, in geometry class, you would just kind of told it.
I don't like that we just did that.
Yeah, like what's the point of using all that calculus when we can just do it with the simple geometry?
Yeah, that's a good question. So other places where this might be more useful, suppose we turn this pyramid upside down,
And then there was liquid leaking out of it.
and maybe there was liquid leaking out, or yes, seriously, that is one, right? We could then track that liquid using calculus.
Okay.
Another thing to think about is suppose this was like some big tank filled with liquid and you dove in and you swam all the way to the bottom
Uh-huh.
And drown.
and you're hanging out there, what would the pressure be down there? Right? The pressure is going to be changing because this is not a uniform volume, but calculus will let us track that pressure.
How
He's
do they
running out of breath.
Wait, how do you track the
Look
pressure
at
in the ocean?
dying.
Is it
Yeah,
just
so
like-
pressure is only dependent on the depth above you
It doesn't have
and the
any.
amount of water up there. If you're in like a square kind of tank, which is the ocean is essentially one giant squarish tank roughly,
Since it's all
Um,
evenly pushing.
it's all evenly pushing down on you. Over here, I've got more stuff at the top because of the shape of it.
Would the
so
pressure
it's-
be more than usual on the bottom compared to a square? Would it be less?
Oh shit, I think it's the same. Okay, so I guess we didn't need calculus for that problem. I'll work harder to find some other applications.
Sorry about it.
It's like he's
Yeah.
drowning.
No, I said it earlier, the pressure is only dependent on your depth, so I guess we didn't need calculus.
Give
for
him
that.
some air. Give him some air.
Yeah, but if we were draining or filling the tape, then it would matter. Yeah, okay, anyway,
Sorry.
Okay.
thanks.
I asked too many questions.
Yeah.
It's good.
Okay,
because then it's
So now it's a matter of taking these slices to build stuff. So we're just going to look at some slightly more complicated problems. Let's see, I had a couple sketched out in my notes here.
So we can't just solve with geometry?
Correct. Problems that you can't just solve with geometry. Yeah, that'll work. Okay, so I'm going to pull one out of your homework. Homework down here. You guys behaving yourselves?
Yes.
It's getting worse.
Wait, what were the results on our?
Oh, I forgot to look those up. Sorry, I was too busy grading and trying to slice stuff up to finish tallying up that data. All right, so here's an Egyptian pyramid you get to check out the volume of. And yes, there's nothing stopping you from using the formula from geometry, but I highly suggest you exercise your calculus skills and give it a try. That's just like it with different numbers. Write circular cone, circular base instead, not a problem. 4, okay, this one I thought was interesting. Yes, this is the one. All right, new page, screenshot. I'll try to do this one together. All right, so spatial visualization is going to be a big challenge here because we need that to kind of get a picture, to get a formula. So we got a volume described by this situation. The base is going to be related to this sideways parabola here, and the line y equals 0, which is the x-axis. And every cross-section of the three-dimensional object is going to be parallel to the x-axis and is going to be a triangle that has the same base as it does height.
Okay.
Cool.
So now we got to try and visualize all this. So step 1,
Feels like a
Graph.
logic problem.
graph. This is the base of our object right here. So we need to graph our base. So instead of having a square base or a circular base, we have a parabolic base.
Awesome.
Wait, how's that work?
How does that work?
Graph it. I'll show you, and I'll try to draw it.
This is
All right.
disgusting.
So sideways parabola.
Does it mean that the
Does this mean, so if it was a real object, would it be like,
it's saying it's a triangle? but the base is a pair.
Yeah, so this is the fun
So wouldn't
part
it
about
not
what we're
be a
doing here.
triangle?
We have 3D printers in the other room, and if we can describe these figures mathematically like this, we can print them.
Oh, that would be cool.
Yeah, so last year, Anne-Marie Hardens, our resident engineer printer, I was able to describe these and then give them to her, and she could print them for us, so we could see, instead of just trying to draw a two-dimensional version of the three-dimensional object.
So do you still have the three-dimensional object?
Can we print this?
Yeah, I've got one somewhere in my office. I'll go see if I can find one in a minute.
Can we print this when we figure it out?
Maybe. Okay, so let's see, 9,
Actually, depending
and
on how big it is,
then
it can take as little as
if-
3 times.
if x equals 0, no wait, if y equals, wait a minute.
Y equals into is a vertical. That would be a
If x
horizontal.
equals 0, y equals 9. Okay, so there's the vertex of this thing over here, and then it opens up this way. And
Wait,
so
what?
if y equals 0, then x is 6. Is that right?
Yes. -6 and 6.
Is it hit
It's
at
negative 6 and
6?
6,
Okay.
yeah.
Oh, yeah.
So here's my parabola.
Oh, you're drawing it sideways.
It is sideways.
Can you make
Is it-
GeoGebra?
Oh shit, that says y equals x squared. I thought it said x equals y squared.
I was so confused.
Sorry.
Sideways.
I don't know what happened to my brain there. Okay. 9, 6, -6.
Wow.
Yikes.
There's my parabola,
Oh yeah.
scaling by 3.
Don't read your line at the bottom.
And then y equals 0 is this guy right here.
Just
All
like a
right,
ship.
so this is the base. Okay, so now we want cross sections parallel to the x-axis. Okay, so here's a cross section parallel to the x-axis. And then coming straight out of the paper or the screen is a triangle. And
Wait.
the triangle has the same height as it does a base.
Oh, I was
Okay.
thinking when you
So
said.
now I'm going to attempt to draw a 3D picture of this.
So how do you determine what the,
Just like my header.
oh, it's the,
At
Nope.
what point does it, wait, what?
This is 9 over
Oh.
here. That's 6 over there.
This is a triangle popping out of the screen.
Wouldn't that still be a pyramid if it was a triangle popping out of it?
I'm very
Okay, so here's the XY plane over here. And then I get this Z-axis coming out. So basically I'm taking this thing right here and I'm bringing it into 3 dimensions and holding it at an angle. And the Z-axis comes straight out of the center here, sticking straight out of your paper or the screen.
Right.
So I've just rotated it and stuck it over here.
Yes, I see that.
Okay. So over here, so here's a cross section there.
Wait.
Here's another cross section there. Here's all those cross sections coming through.
So when did,
So
But did
over
not
here,
be
this goes from
triangle.
-6 to
that's what I'm
6.
saying.
So all the height is 6?
So
no, height
no,
of 12.
-6 to 6 would have a height of 12. So then I'd have to go up the z-axis, 3, 6, 9, 12. So then here is the triangle at one end of this.
Okay.
At the other end of it, it zeroes out here. And then somewhere in the middle, right, there's going to be a length of like 4. So maybe this one right here is 4 out in each direction. So it would be 8 tall. So if I go straight up from here, 3, 6,
The parabola is.
8 would be about here. So this would be that triangle right there.
It's not
roughly.
3D. The parabola's flat.
Oh, okay.
Can you picture this? Are you having a hard time picturing it?
No,
It's not like that.
I'm good, but when you said the parabola is the base, I immediately thought like diamond. Like the parabola was also 3D, like,
No, no, no,
So,
no.
like, it's like,
This
That's
is,
but it's flat.
I'm having
It's
a hard
flat.
time
It's just the
imagining.
base.
so
Okay, I see.
here, this is the bottom of my pyramid.
Okay,
That's
like
the
it's like an
bottom of the
iron.
pyramid.
It's like an iron.
okay.
and we could like imagine.
And if you flip it over, so you're looking at it from straight above, there are triangles, cross sections coming straight out here. And that's what I'm trying to draw over here.
And so,
Okay.
like,
So
so
this
like,
is, this is, so like, this is sitting on the
Would it
ground.
be like
In the
kind of
middle,
like
from the
front,
bottom.
like the tip of someone's shoe,
Yeah.
except pointed
in
at
the-
the top?
in the
Yes.
middle.
So this is like the
Yeah.
tip of a
So
shoe.
it's like-
Yeah, this is like the tip of a shoe here. And then
instead
it's
of-
coming out, I need a different color.
Interesting shoe.
So
And
then the
then
shoe
there's a
has
line.
this beautiful seam. The
Okay.
shoe has this beautiful seam down the front of it.
Yes.
Beautiful.
Yeah, beautiful seam. It's,
Is it
Not
natural
bad,
shape?
not bad.
No, because it's not an actual shape. This is somebody sat down and said, how hard can I make a set of calculus students work?
yeah, so if I draw some, if I erase some of this inner structure here.
I think you're just making it worse.
I feel like that's also worse.
I'll
I
just
think it's
think of it
not-
like a really fancy dress shoe.
It looks like an iron to me. You know when you iron your clothes?
Mhm.
Except
That's
it's
Yeah, this is
yeah.
iron. There you go.
Yeah, oh yeah, it's like shaped like an iron, right, yeah.
Except
More
instead,
size.
except instead of the top of the iron rounding out, kind of, it's like pointy.
Okay,
That's
so
a
that's,
problem.
that's the shape we're trying to build.
Let's get a
It's a
red
shark.
So maybe,
That's what I was thinking. Just a-
This little fin sticking up.
It's
the
a shark.
axis.
yeah,
It's a shark.
And the reason it works is because as the base
we're
is
not
getting
artists.
smaller, it's getting shorter.
yes.
Okay.
Yeah, so this is its tallest way back here, and it goes to 0 right there
Yes.
at the vertex. It goes to 0 right there.
Okay.
Yeah.
That makes more sense.
Okay,
So
when it
this is,
goes-
we could give this as a shoe design for Nike. Please make us a shoe with the shoe. And
What's
they
the
can totally
volume of
whip
your
this out.
shoe?
Okay,
We can
so,
integrate your shoe.
all right, okay, focus, come on. We're gonna get this done. So for me to do this, do you have to draw the 3D picture? No. But you've got to draw the 2D so you know what part of your cross-section looks like. Because we need the dimensions of that cross-section. We need to figure out how long that line is, because that's going to be the base of a triangle.
Does it matter where you put that
But how,
line?
what,
So that's going to be the base of some triangle right here. The height of the triangle is going to be equal to the base. Okay, so let's see, to figure that out, well, that's the distance from this point to that point horizontally.
okay, but we don't know what those points are.
And so the distance from here to here is just that value for x.
Yeah.
Yeah.
So there, I have a formula that says y equals 9 minus 1/4 x squared. I need it as x equals instead. Because the thickness here is a dy, isn't it?
Yes.
Yes.
Yeah. So I need to solve for x up there. So that's going to give me y minus 9 equals negative 1/4 x squared. Multiplied through by negative 4. It's going to give me negative 4y plus 36 equals x squared.
Take the square root of all of that.
Take the square root, and we get x is equal to plus or minus, and then a square root, and I'm going to write it as 36 minus 4y. For some reason, that makes me happier. I'm not sure why. So plus the square root is this side,
Minus the square root.
and minus the square root is the other side.
Okay.
Which basically means is if this right here is the square root, the full length is double that.
So when they, when
So I've just determined that, hang on one sec, Bruce. The base then, I believe, is twice that square root of 36 minus 4y. Okay, what was your question? Was that it?
Kind of, that's fine. I figured it out.
Okay. Sorry, a little messy there. Clean that sucker up. Minus 4y. So that's the base. What's the height of this thing?
Same.
The same thing. That's the height of it. Okay. So that's the height of it. I'm going to take this to a new page. So my cross section is a triangle, right? And a triangle has an area of 1/2 base times height. So for me, that's 1/2 twice the square root. And the height is also twice the square root. It's in our advantage, it's advantageous for us to clean that up. So 1/2 of 2, I love that. This 2 is hanging out. Square root times itself cancels the root. So this is the cross-sectional area. So now what I want to do is add up all of those cross-sections.
Yeah.
That's, well, in this case, be dy. Yeah, so to add these up, I use the definite integral. So I want to integrate as y goes from 0 to 9, I believe, was the peak of that parabola. Of twice 36 minus 4y dy gives me the thickness of each of those slices. Yeah, that's not too bad.
So you have to.
So the hard part of all of these is getting all that set up. Once you get that, it's like, no problem. This is the easy part.
This is why I really agree.
Okay, so I'm gonna write the antiderivative down, and I'm gonna show you my trick for plugging it into Desmos or GeoGebra, which will make all of you make less errors, hopefully. Will help all of you make less errors. So antiderivative here, the 2 is just chilling out. I'm gonna get a 36y. Don't forget parenthesis there, that's important. And then minus 4y squared equals what, 2y squared? 2y squared. Minus 2y squared. And we, ooh, that got weird. We have to take that from 0 to 9. And sometimes the boundaries are 0 and some number, other times they're funky numbers. It just kind of depends on the problem. Yeah, the 0 is going to fade away on this one. So this is an easy one to do by hand, but I'm going to bring in the calculator just anyway.
Bless you.
Bless you. So my, this is now, I'm going to call it v of x because it's a volume function, is what it turned into. And v of x is equal to twice parentheses 36. I got to use x, can't use functions of y in Desmos or GeoGebra, minus, was it 2x squared? And I always mistype these with y's, so again, you gotta, when you're sideways, you gotta rethink. That's my formula, right? Yeah, so now I just want to know what's v of 9. So then I go, hey, what's v of 9? Okay. 324. Not that I don't want you guys occasionally practice your arithmetic skills too. You know, that's a good thing to do sometimes. But you got to draw a picture.
So pictures.
So at least, so pictures are going to be required. Yeah. So I'm going to say, set this volume up. I want to see a picture of, and usually what I want to see is I want to see a picture of the base and I want to see a picture of the cross section. If you think you can take it farther and try and make a 3D rendering to the best of your ability, give it your best scribble, you know. It does do 3D graphing, but telling it how to do a 3D graph is a whole nother epic adventure. So,
Really?
yeah.
Oh, lovely.
Yeah. Yeah, because you got to tell it not only what to do with X and Y, you got to tell it what to do with Z. Right. So off the top of my head, I'm not exactly sure how to tell it how to draw this for me with Z, but if I fiddle with it for 10 minutes or so, I'll figure it out. And then the next one will be easier. Next one I'll be able to do in 2 minutes. But I haven't done one in a while. All right. So we did it. That wasn't too bad, was it?
No, it
A little bit?
And we could use all of those visualizations in the areas to figure out how to print that.
Yes.
You need a printer.
Well, just like it's, you got to think about how I would tell GeoGebra to draw this. I would also have to think hard about how to tell the 3D printer to draw it too. So it's not trivial, but it's doable. Yeah.
But we're only using geometric shapes, right? Can we do this with like regular shape?
Yes, you can. Yeah. So that means you would have an equation for how the cross section could change in 2 directions. That is possible. Which means you have to get each of those directions right. So let's try something like that since you brought it up.
Big door.
Good job.
Wait, I missed
We have
something.
8 minutes.
Okay. So let's, we're going to do a relatively easy version of what Vitor asked, which is kind of almost lame, but it's not too bad.
Wow.
We're going to do that was quite the lead up to this problem. Pyramid with a rectangular base instead of square. And so let's say the rectangular base is 2 by 3, and the height is, let's go with 5. All right, so I'm going to just draw my best 2 by 3 base. So here's my base viewed at an angle, and then from the center I have to come up 5, so maybe 5's about that high. So there's my pyramid with a little altitude drawn in there. So it's 2 by 3, and the height is 5. Not the diagonal, the height is 5 here. So then what I have to do is I have to figure out a formula for the cross section. Now, yes, you could cheat and use the geometric version of the formula. But I'm just going to show you a method that will help with problems that are a little more irregular than this one.
When you use the section out of the middle, can't we just use the base?
Yeah, I'm just, usually, well, yes, but the cross sections that I'm taking are going to be moving up through the height, right? So I always like to draw one of those cross sections. And I kind of use my base as my model, right? I'm parallel to that edge, I'm parallel to that edge. So this right here is one of my cross sections. So I need a formula for how wide is that cross section there and how wide is the cross section there. It's just like we did before, I just have to do it in 2 stages. So one view of this is to put the vertex at the origin. I'm going to put the 5 over here. And then for the 2, I'm just going to come up 1 unit on each side. So then if I just looked at it head on from the 2 side, then that face would look like this right there. Oops, I drew it backwards, sorry. I meant to have it come out of the origin, the point. So that right there is the 0.51, and this down here is the 0.5 -1. So I just need an equation for that line because that tells me how the side changes. So the side's going to change here. That slope is what? 1/5? All right, so that gives me that height right there. I need to double that. Okay. So let's call that the width. Right there. So my width is 2/5 x. For the side of 3, I'm just going to repeat that. It's got to go 5 high. And to get the 3, I'm going to go 1.5 up and 1.5 down. And I'm going to put my base over here-ish. So this would be up 1.5 and then over 5. So you could say it's y equals 1.5 5x.
Would be the length.
What's that?
The length.
Yeah, so this would be the length. Yep, thanks. And that y is just that height right there. So I need to double that also. So if I double 1.5, I get 3. So I get 3/5 x. And if you look back at the picture, doesn't it make sense that I'm going 3 by 5? So the ratio of the height to the width is 3 to 5. And here, this is 2 versus 5, so the ratio is just 2 to 5. And so after you do a few of these, you just see, oh yeah, it's just proportional, base by height. So then this is a rectangle, right? So then the area of that rectangle, my cross-sectional area, is just the product of those two. So 2/5 x times 3/5 x. Or 6/25 x squared. So then I want to add up all of those cross sections. What do I use to add up all those cross sections? The definite integral. So then my volume would be the integral from 0 to 5 through the height of that. What was it? 6/25 x squared dx. Yeah. So the hard part is the setup. The nice thing is that since this is just a straightforward pyramid, I can check my answer using geometry. Right? But there's going to be some others where we don't have geometry formulas that we're going to have to figure out. So we are going to do one more fun thing with this, but I'm just going to set it up today and do more of them tomorrow. Finishing that one's easy, right? You can find an derivative, you can plug in the boundaries. So we're going to take the slices a step farther. We're going to do rotational slices. So the way a rotational slice works is you have some profile of your image. So let's say here's my function f of x right there, and I'm going to stop at some value there. Let's call that b. And then what I want to do is I want to spin the x-axis. So anybody ever done pottery with a wheel?
Yeah.
Yeah. This is a pottery wheel. Okay.
Oh.
We're spinning around the x-axis, so this would be the base of my pottery wheel. And then this object is going to become 3D. So I'm going to create a parabolic dish if that were a half of a parabola.
Okay.
Okay. So say, like, if it's sideways, then maybe my f of x here, maybe it's the square root of x. So if I do that, what does a rotational slice look like here? If we slice through, well, that rotational slice is just going to be a circle, isn't it? And all I need to know is what's the radius of that circle? In this case, the radius is my y value, and y is the square root of x. Yeah, that would be my radius here. So once I know the radius, the area of a circle is just pi r squared. So if I were rotating the square root of x, then my cross section here for some x value would just be pi times the square root of x squared, or simplifying nicely to pi x. And then all I have to do is add up all of these disks. And how do I do that?
Integrate.
Integrate. So I would just integrate that. In this case, as x goes from 0 to whatever I told it to stop. Yeah. So that's, these are slices, but they're slices based on a rotation, which means all of the slices are circles.
Well, that's not.
And all we have to do is figure out the radius. Yeah. Yeah. The fun happens when we try to turn these circles into washers, like hollow out the middle, like drill a hole through the center.
When you actually start making
Oh, is anyone?
So I
when you
can
just
turn this into a
when you just-
parabolic cup or bowl.
when you just integrate,
How much clay would I need?
when you just integrate the inner circle,
Hey, oh,
Yeah.
and then-
Yeah, you would just integrate the inner circle and
And
take it
it's
away from the upper circle. Yeah, it's
But
just
then,
subtraction.
so it's.
So we're going to spend the next few days doing this.
yeah, I noticed the homework wasn't due until the 5th, and I went, oh, we're gonna spend a while.
It's going to take a while.
it's gonna take a hot minute.
Yeah, sorry, Daphne, what were you saying?